In this next part, we are going to discuss the molecular shape. Um, Now, why do we need to know about shapes? Because the shape determines reactivity. And if you guys are interested more in this, we can discuss this next time we meet. I can tell you all about how the shape determines reactivity. The model we are going to be using for this is known as the valence shell electron pair repulsion theory, where the way it works is going to be as follow. We're gonna look at the distribution of how many electron pairs are around the central atom. And based on how many groups we have, we're gonna say because they're all negatively charged, are going to push each other away in order to minimize repulsion. By doing so, they're gonna adopt a geometry, a nice distribution around that central atom. So when we say geometry, we're actually interested in the distribution of the outer atoms relative to that central atom. All right? But we always gonna take into account whether the electrons are bonding or not, because they're still there and they are still negatively charged. Okay? That's what determines the shape. So for example, we can look at the following hypothetical molecule and determine how many electron groups exist around it. And the way we do it is by counting in each side how many we have. Okay? And it doesn't matter whether they're double bond, single bond, or triple bond. This double bond right there count as one electron group. This single bond is another, this single bond is another, and that lone pair right there counts another electron group. So in total, we have 4 electron groups. And that's the way we look at it. So whether you have double, triple, or single bond, all of them count as one electron group. Whether you have a lone pair or a single electron on one side, it does count as an electron group. So this central atom has 4 electron groups. And based on that, we can use the VSEPR model that's gonna pull. So in this case, if you have 4 of them, you get a structure that is similar to this, where they're actually pulled all over the place, all right? Farthest away from each other. So based on the electron group geometry, there are 6 electron group geometries. In Chem 10, we're gonna look at the first 3. There are 5 of them, and we're gonna ignore the other 2. Okay. So even though there's 6 electron groups, we can have 2, 3, 4, 5, and 6. We're gonna ignore the 5 and 6. So we're gonna look at 2, 3, and 4. And based on the number of electron groups, we're going to determine the distribution, but that's what we call it, the family. But that doesn't mean that the molecular geometry is going to be the same. For example, in here we have one lone pair. That lone pair cannot be visualized, but it will affect the geometry. So when we talk about molecular geometry, we're talking about bonds only. When we talk about electron geometry, we're talking about everything including the lone pair. And we need to be able to differentiate between the two. Okay? Let's start with the linear electron geometry. When we have 2 electron groups, let me see if I show you what I'm talking about here. Okay, so when I have 2 electron groups, let's say I got 2 lone pairs. That's one, and that's another lone pair. Notice, no matter which way I move them, they still repel each other to give me a linear geometry, 180 degrees. So you end up with a bond if they're bonding. So let me get rid of the lone pairs and put bonds in that. So for example, let's say I have CO2 instead. See, do I have CO? Yep, CO2. Okay, CO2 I have two electron groups, no lone pairs, right? Two double bonds, that's two electron groups. The geometry is going to be 180 degrees. Okay, the bond angle right here is going to be 180 degrees. So the electron geometry is linear and the molecular geometry is linear here. And the bond angle is 180 degrees. All right, so we have a 180 degree bond angle. That's linear geometry. Okay, that's the electron domain group for that, linear, 180 degrees. Now, even if you have only two atoms, you can still call it linear geometry, but what we're going to worry about here is when we have at least three atoms. But if you have two, like HCl, it's obviously linear, right? That's the only geometry they can adopt. Now let's take a look at the second electron domain, that we have three electron groups. So when we have three electron groups, the electron geometry is going to be called trigonal planar. Okay, we're going to call that trigonal planar. Let me share with you again. Let me go back up. Okay. So in this case, I'm going to use a model instead. And I'm going to use 1, 2, 3 electron groups. You see how it is in the plane? If I move it, all the electron groups are in the same plane. Okay, that is trigonal planar. Okay, in the same plane. Let's look at an actual molecule. So now if I have three molecules, they're in the same plane, and a bond angle is 120 degrees bond angle. So within this electron group geometry, I can have two different molecular geometries. If I have no lone pairs like I have in this scenario right here, then the molecular geometry is the same as the electron geometry. We're going to call it trigonal planar. But what if I have one bond less and I have a lone pair instead? Notice that even though I don't have an actual bond, but that electron cloud is still there, and you get the bond angle to still be around 120, so that electron right there is still affecting the molecular geometry. So when you have an electron geometry that is trigonal planar and you have one lone pair, then the molecular geometry will be called bent. Okay? It's called bent geometry. Okay? That is a bent geometry. Let me see if I can find you an example here. Okay? That's a bent geometry. Okay, it's trigonal planar with bent geometry. This is SO2. Okay, will give us one lone pair on sulfur with two double bonds. That is a bent geometry. Okay, let me recap. When we have three bonding groups, zero lone pair, then the molecular geometry is also trigonal planar. One example of this will be BF3, bond angle 120 degrees. If we have one lone pair, that electron cloud is still there and it will affect that geometry, but that geometry is called bent geometry. Okay, so we have two molecular geometries in this electron group, trigonal planar or bent geometry. Now let's take a look at the next. Now let me say that the presence of electrons have an effect on the bond angle. Because in a bond, the electrons are localized between two nuclei. In a lone pair, they're close to the nucleus of bonding. It's going to push even further on and it's going to make the bond angle less. So for you, when we say here 120, in this scenario, you don't have to tell me how much smaller it is, but you should know that it's less than 120 degrees. That's all. That's all I ask of you, just to recognize that it is less when you have a lone pair. Okay, let's not worry about exactly what it is. Now, the third domain we're going to look at, this is when we have 4 electron groups. So when we have 4 electron groups, we're going to look at 3 different molecular geometries. So let me pull out the sample again. There we go. Okay, so we're going to have 3 different geometries. So let me cancel the bond and put 4 electron groups. 2, 3, 4. All right, so we have 4 electron groups. It's going to adopt the following distribution. See how it is? This is known as tetrahedral geometry, electron group geometry. That's tetrahedral electron group geometries. So if I have 4 bonds, you'll end up with the following electron group geometry. Okay? 4 bonds, no lone pairs, then it's tetrahedral, bond angle 109.5 degrees. In this particular electron group geometry, we have 3, like I said, 3 molecular geometries. 1 with no lone pairs, or I can have 1 lone pair. Okay? Notice it's still tetrahedral distribution of the electron groups, but the geometry now is known as trigonal pyramidal. Okay? With a bond angle less than 109.5. Trigonal pyramidal. And next I can have 2 bonds with 2 lone pairs, and you'll have a bent geometry. Okay? You'll have a bent geometry. These are the 3 molecular geometries that exist. So let me reiterate this one more time. We have 4 electron groups, all 4 of them are bonding. Then the electron geometry is tetrahedral, molecular geometry will be tetrahedral as well. An example of this will be methane, CH4. No lone pairs, all bonds. But if I have 4 electron groups where 3 of them are bonding and 1 lone pair, like the case in ammonia, okay, let me zoom in on ammonia here for you. Like the case in ammonia, you will notice that in the case in ammonia, right here, you have 1 lone pair, 3 bonds, it'll give us trigonal pyramidal with a bond angle less than 109.5. But if I have 2 bonds and 2 lone pairs, then we will have a geometry that is a bent, tetrahedral bent geometry, like in the case of water, right? When you draw the structure of water, you'll see that it has 2 lone pairs and 2 bonds. Therefore, it is bent, tetrahedral bent geometry. Now, when it comes to doing your lab reports, you're going to have to represent these in a 3D. So how do we present molecular geometries on paper? What we do is, if it's in the paper, in the plane of the paper, we use a straight line. If it's projecting into the paper, we use the hash line. And if it's out of the paper, we use a wedge. For example, if I'm looking at CH4, okay, it's tetrahedral. So you would draw it something like this. That's in the paper. Then I'm gonna draw one that is pointing away from me, that's hydrogen, into this, and one that is pointing at you, as such, CH4. Okay? That's how you would draw these molecules. On this page right here, this is from your textbook, you can use the following convention when you draw molecular geometry. So on your lab report, you're going to be drawing using the following convention. Please do not follow the instructions in your lab handout, this is what I want you to follow. So I don't want any of you to draw any lone pairs when we talk about molecular geometry. So let's recap. How do we predict geometries? Step one, you need to draw the Lewis structure, which we already spent too much time on that. So you need to learn how to draw the Lewis structure. Step two, you need to count the regions of electron density around the central atom, including lone pairs or double or triple bonds. You need to figure out how many electron groups you have. Then based on that, you determine the electron pair and molecular geometries. You know they're not the same, right? They can be, but they don't have to. So if you have two electron groups, then both electron and molecular geometries are going to be linear and we'll have a bond angle of 180. If we have three electron groups, then the electron geometry is going to be trigonoplanar with bond angle 120. But if I have no lone pairs, then the molecular geometry is trigonoplanar. But if I have one lone pair, then we're going to call it bent or angular. Then if we have four regions of electron groups, then the electron geometry is tetrahedral with a bond angle of 109.5. If we have no lone pairs, then the molecular geometry is tetrahedral as well. If I have one lone pair, then it's trigonoplanar. And if I have two lone pairs, then it's bent or angular as well. Okay? And make sure you know how to sketch this wedge and dash diagram. Table 10.1 is a really nice summary of what I just said. So exactly what I just told you on the last two slides is in here in this table. So that was going to be your reference. Study that table very well, understand it, and memorize it. Okay, let's take a look at an example. Draw the wedge and dash diagram of nitrogen trichloride. Okay, so we need to draw the wedge and diagram. So that means we need to draw the Lewis structure first, then determine its geometry. So Lewis structure. Nitrogen has 5 electrons. Chlorine has 7. I have 3 of them. That's 21, total of 26. Then I'm going to draw nitrogen has lower electronegativity than chlorine. Will be something like this. This is the skeletal structure. That's 6 electrons, so I have 20 left. You go 2, 4, 6, 8, 10, 12, 14, 16, 18. So 18, so I have 2 left. I put them on nitrogen. Now by looking at this, I see that I have 4 electron groups around nitrogen. That means my electron group geometry is tetrahedral. All right, it's tetrahedral. Then, when I look at my molecular geometry, I have 3 bonds and 1 lone pair. So I go right here. It's tetrahedral. I have 4 electron groups. So it's tetrahedral, but I have 1 lone pair. Therefore, it's trigonal pyramidal. Okay? It is trigonal pyramidal. So that would be my geometry, trigonal pyramidal, and it will have the following wedge and dash diagram. I hope that makes sense. What if I have larger molecules? When I started talking about the geometries, I stated that we are interested in the distribution of atoms around one atom, what the distribution are. So when we talk about geometry of larger molecules, we're going to follow the same convention. I'm going to pick one atom at a time, and I'm going to see what's the distribution around it. So when I look at this carbon right here, I have 4 electron groups. So the electron geometry is tetrahedral, and the molecular geometry is tetrahedral as well. This carbon, I have trigonal planar because I have 3 electron groups. Molecular and electron geometry is the same. Trigonal planar, 3 electron groups. Around oxygen, I have 4 electron groups. So the electron geometry is tetrahedral, but the molecular geometry is bent because I have two lone pairs. That's the way we approach larger molecules, one atom at a time. So when you draw it, it'll be drawn something like this. Okay. Um, Go ahead and pause the video here and figure out what are the structure around each of these atoms within glycine. So you're going to determine it for nitrogen first, then carbon, then this carbon, then that oxygen. All right, so what do you do? We look right here. This nitrogen has 4 electron groups. Electron geometry is tetrahedral. I have 1 lone pair. That means the geometry is trigonal pyramidal. Carbon, 4 electron groups, no lone pairs, then it's tetrahedral. Carbon number 2, I got 3 electron groups, no lone pairs, then it's trigonal planar. Oxygen, I have 4 electron groups, 2 lone pairs, then it's bent. So you'll end up with the following geometries. Let's try another one. Go ahead and pause the video and try this one on your own, then come back and check your answer. Predict the molecular geometries in boric acid. Now this is acid, it's an oxyacid. That means the hydrogens are attached to oxygen. Boron is the least electronegative. That is going to be the central atom. Let's count the electrons. I have 3 electrons for boron. I have 6 for each oxygen. I have 3 of them. That's 18. And I have 3 hydrogen. That's 3, total of 24 electrons. So we have the following Lewis structure. I have 3 electron groups on boron, and there are no lone pairs. The shape is going to be trigonal planar on boron. I have 4 electron groups on each oxygen, with each having 2 lone pairs, so 2 bonds and 2 lone pairs. Then the shape on oxygen is tetrahedral bent, and we should have the following shape. All right, that is how we predict molecular geometries of molecules. And the last part of this chapter, we are going to look at molecular polarity. If you recall earlier in this chapter, we discussed bond dipoles. So if we were to look at this right here, the bond between carbon and oxygen is polar, right? But when we look at the electrostatic potential map, we see that CO2 is non-polar. Even though the bond is polar, the molecule is nonpolar. As a matter of fact, the net dipole for this molecule is 0. It's nonpolar. So I have polar bonds, but the molecule is nonpolar. When I look at water, I have also polar bonds, but in this case, the molecule is polar. So why is it that the molecule, such as water with polar bonds, is polar, whereas a molecule like CO2, that even though it has polar bonds, it is non-polar? It has to be due to the shape of the molecule, right? They both have different shapes. Because they have different shapes, then the polarity of the molecule has to do with the shape. So in order for a molecule to be polar, it has to have what we call an asymmetrical distribution of charge, resulting in polarity. It has to have asymmetrical distribution of charge. So when we talk about polarity of molecule, we're talking about if we were to take that molecule, put it in an electrical field, it would line up. The more electronegative part of it will point toward the positive plate, and the less electronegative atoms point toward the negative plate. So when we discuss polarity, what we're going to do, we are going to apply what we call symmetry. If your molecule is asymmetrical, if it's symmetrical, then it's going to be non-polar. If the molecule is asymmetrical, then it's going to be polar. As simple as that. All right, what are the symmetrical molecule? What do we mean when we say symmetrical? So when I talk about symmetry, I'm talking about perfect geometry, no lone pairs, since we did not discuss these, so you can ignore those. no lone pairs, and identical outer atoms. We must have identical. See, all atoms, outer atoms must be identical in order for that pole to cancel. So when we look at CO2, it's linear, it's symmetrical. The outer atoms are identical, therefore they cancel out. My molecule is polar. But if I look at water, it's not symmetrical, therefore it's non-polar. But that's not always the case. Sometimes we can have atoms that are um, asymmetrical, but they can still be non-polar. So let me give you um, here. Let me do the following. Show taskbar. Let's do the following. Why can't I erase this stuff? Let's erase, 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 clear. Okay, doesn't want to clear. Whatever. All right. You can ask yourself, is the molecule symmetrical? If you answered yes, then it is automatically non-polar. If we answered no, then we should ask ourselves another question. Do we have a lone pair? Do we have a lone pair of electron? If you answered yes, then the molecule is polar. If you answered no, then you're going to ask yourself another question. Oops. That we're going to ask ourselves another question. How can I move this up? So we can ask another question. Do we have a polar bond? Then we look at, I'm going to go up here. If we answered yes, then the molecule is polar. If you answer no, then the molecule is non-polar. I think that's the best way of determining polarity. Okay, so let me recap this, go over it again one more time. We ask first if your molecule is symmetrical. If it is, then you're done. It is non-polar. But if the molecule is not symmetrical, is asymmetrical, then what determines its polarity is the following. If it has lone pair, then even if it's asymmetrical, it's going to be polar. But if it doesn't have a lone pair and it doesn't have polar bond, it's going to be nonpolar as well. Okay, keep that in mind. It'll be nonpolar. Those are the conditions for polarity. So let's take a look at the following. NH3, it's asymmetrical and it has a lone pair, right? There is a lone pair on nitrogen. Therefore, it is polar. Even though it has a polar bond, I don't need to ask if it has polar bonds or not. Let's take a look at here. HCl, asymmetrical, and polar bond, polar. CCl4, it is symmetrical, nonpolar, even though it has polar bonds. On the other hand, CH3Cl, it's asymmetrical, no lone pair. It has one polar bond that makes it polar. BF3 is asymmetrical, it's symmetrical, that's automatically nonpolar. NH3, it's asymmetrical, it has lone pair, therefore it is polar. All right, let's take a look at an example. Decide whether the following are polar. So you should pause the video, use those electronegativity values, and determine if the following molecule is polar, the following molecules are polar or not. Let's look at the GI. It's trigonal bent. Those are the electronegativity values. I have polar bonds. The molecule is asymmetrical, and I do have a lone pair on nitrogen. Therefore, the molecule is polar. Now let's take a look at SO3. Even though I have polar bonds, the molecule is symmetrical, and it is therefore nonpolar. I want you to be very careful. You might look at the double bond right here and think that the double bond belongs, let me change color of my pen, that the double bond here belongs to only one. So you need to keep in mind that we need to draw two more resonance structure for this, where we put a double bond on this oxygen and a double bond on that oxygen. That means the true structure in nature, which you have a hybrid resonance, you have equal bonds between sulfur and all three oxygens. The bonds are equal. Therefore, that makes that molecule symmetrical. All right. And that will conclude our discussion with covalent bonding. The last thing we're going to talk about very briefly is bonding in metals. I don't like this model, but that's the model your textbook mentions. So the way you'll look at bonding in metal as if you take all metal atoms, and what they do is they actually shed their valence electrons, and you end up with cations swimming in a sea of electrons. That's bonding in metals, and that's all I'm going to ask you to know about this. This would allow for the existence of metal alloys, and there are two types of metal alloys, and I'm going to hold you responsible for these. There's substitutional alloy and interstitial alloy. Substitutional alloy is when you take your sample, remove some of its atoms, and substitute for similar size other metal atoms in there. So for example, if you want to make brass, you remove some of the copper and replace it with zinc, you end up with brass. That's an alloy. On the other hand, interstitial alloy, if you recall in the beginning of this chapter, we talked about how ionic compounds actually give rise to crystalline lattice. So whenever we talk about a lattice, the way things, if you think of spheres when they pack, there's always an empty space between them. So if we were to bring a metal and fill the empty space, by filling the empty space, you're maximizing interaction and strengthening the interaction. And this is known as interstitial alloy, where you fill these interstices or the holes. So for example, if we take iron and add some carbon to it, we can make steel. That's an alloy. All right, and that is a wrap for this chapter.